A case which could be simplified easily, because those cases we talked about, they're integrals and they're complicated, and then they depend on the PDF. But if you have sufficiently large number of levels, if you allocate enough large number of bits and your errors are very small, so we could simplify those formulas. We could approximately simplify those formulas. In this case, let input to be in an interval instead of minus infinity to plus infinity, because in any way, if you get audio signals or video signals, the value of voltage is never minus infinity or plus infinity, so you have bounded values. Suppose that x is a zero mean random variable with a PDF of fx, and assume that you allocate L level of quantization. So we quickly conclude that delta, which is the distance between the quantization levels, should be 2x max divided by L, because the overall support of your signal is in this area. So you have here a minus x max, and then you have x max, and then you want to divide these by L subintervals, assuming that these guys are all equal to delta, and you have L of them, so L delta should be equal to 2x max. So therefore, delta is equal to 2x max divided by L. So it is easy to show that if the number of levels is sufficiently large, the quantization error, which is the difference between the input signal and the quantized value, has a uniform distortion with a support of delta. So it is obvious that the mean of the error is 0, and its variance is equal to integral from minus delta over 2 to delta over 2, and if you calculate it, you get delta to the power 2 divided by 12. If you replace delta equal to 2x max divided by L here, you get x max to the power 2 divided by 3L to the power 2. So obviously, if you increase the number of levels, the distortion power reduces. The number of levels is equal to 2 to the power of r, and r is the number of bits that you will allocate to each of your samples. Because, for instance, if you allocate L equal 8 levels could be characterized by 3 bits. So r is the number of bits per symbol, and L is the number of levels. So L is equal to 2 to the power of r. So I could have put here x max to the power of 2 divided by 3 times 2 to the power of r to the power of 2. So something like that. So obviously, if you plug this value in your SQNR is the ratio of the variance or power of your signal divided by variance or power of the quantization error. So what you will get, sigma 2x comes here, and sigma 2e you replace it here. So just you put this guy in here and then simplify it. So you will get 3 times 2 to the power of 2r becomes here, x max goes in the denominator and the noise power. So this is a formula that we use when the number of levels is very large or sufficiently large. Because we usually, when we deal with the power of signals or power of noise and so on, we often talk about dB. If you take 10 log 10 of these, the unit of these, because this is unitless, this ratio, because this is power unitless. So if you take 10 log 10, we call it in dB. So this is same equation as this one, just to take it. Quite often as engineers, we don't write this one, just we say SQNR equal to this expression. We don't write this, but we mean that there is a 10 log 10 dB. So the only thing we say here, we say in dB. This is, we are used to, as engineers, to be not accurate. So SQNR is 6.26 0.02 R, which is 10 log 10 of this guy. And then you will have 4.77, which is 10 log 10 of 3. And then 20 log 10 of, on the basis of 10 of this ratio. So what we see here is that the signal to noise SQNR increases exponentially with the number of bits. So if you allocate every extra bit, will lead to about 6 dB improvement in signal to noise ratio.